It's really amazing. Some of the stuff you sent over on string theory
Oh, yeah.
really makes you think, like, what if the universe is kind of like a giant symphony
Uh-huh.
where everything we see and touch is like the music coming from these tiny vibrating strings?
Right.
So today we're going deep into this mind-blowing idea.
Yeah.
I brought in an expert to help us break it all down.
Well, it's definitely a different way of thinking about things, for sure. String theory really challenges how we see the universe. Like, instead of particles like electrons and quarks being like the fundamental building blocks, it's saying these super tiny vibrating strings of energy are.
So I guess let's start with the basics. How do these string vibrations actually work?
Okay.
I saw that the sources mentioned this violin analogy. Is that a good place to start?
Yeah, that's a great place to start. So think about how, like, when you play a violin string, you can get different notes depending on how it vibrates.
Right.
It's similar in string theory, except different vibrations of the strings create different particles and forces. So instead of like a universe built from static pieces, it's more like a universe that's always in motion. A cosmic dance of strings, you could say.
I see what you mean. I'm already seeing how this could bring together some of the big ideas in physics.
Uh-huh.
The sources talked about a conflict between Einstein's theory of relativity and quantum mechanics.
Right.
And how does string theory try to bridge those two?
Well, you've hit on one of the biggest motivations behind string theory, the idea of a theory of everything. You see, general relativity is great at explaining gravity on a big scale, planets, stars, galaxies. But when you get down to the super small world of particles, quantum mechanics is king. And for decades, physicists have been trying to find a way to fit these two together.
So it's like they're speaking two different languages.
Exactly. They describe the universe at totally different scales with different sets of rules. String theory tries to bridge that gap by suggesting that gravity, the force that shapes the cosmos, is just another vibration of those strings, like a deep bass note in our cosmic symphony. This could bring gravity under the same umbrella as the other fundamental forces that are described by quantum mechanics.
Okay, this is where things get really interesting for me.
Yeah.
The source material mentions that string theory needs more dimensions than we can see to work.
Right.
That sounds pretty wild.
It's definitely one of the most mind-bending parts of string theory. The math only works if there are at least 10 dimensions, maybe even 11. But of course, we only experience 3 spatial dimensions and 1 of time. So where are all these extra ones hiding?
Yeah, if there are all these extra dimensions, why haven't we noticed them?
Well, think of it like, imagine a garden hose stretched out long. From far away, it looks like a one-dimensional line. But if you get closer, you see that it also has a circumference, a second dimension, curled up tight. String theory proposes that these extra dimensions are curled up at super tiny scales, billions of times smaller than an atom. They're woven into the fabric of space, but just too small for us to see with our current technology.
So they're like hidden in plain sight. But if they're so small, how can scientists even think about studying them?
Well, it's a huge challenge. One way is to look for indirect evidence.
Go.
For example, at the Large Hadron Collider, physicists are smashing particles together at super high energies, hoping to create particles that could briefly leak into these hidden dimensions and leave behind some kind of signal.
Sounds like looking for a needle in a cosmic haystack.
Yeah.
But I can see why physicists would be so excited about the possibility. But let's step back for a minute.
Okay.
Is string theory all just theoretical? Does it have any practical implications in the real world?
That's a question that comes up a lot, and it's a good one. It's true that string theory is still mostly theoretical, but it's been the driving force behind some amazing breakthroughs. For one thing, it's pushed the limits of math, leading to new tools and concepts that are being used in things like computer science and cryptography.
So even if we can't directly prove string theory,
Yeah.
yet it's still pushing science forward in other ways.
Absolutely. And beyond the math, string theory has helped us understand some of the most confusing mysteries in astrophysics, especially when it comes to black holes.
Oh yeah, black holes.
Yeah.
Now you're talking. These cosmic enigmas that gobble up everything in their path. So how does string theory help us understand them?
Well, one of the biggest puzzles about black holes is something called the information paradox. It asks, where does information go when it falls into a black hole?
Okay.
Classical physics says it's lost forever, but that clashes with what we know about quantum mechanics. String theory offers a solution by saying that information isn't lost, but instead it's encoded on the surface of the black hole.
Wait, are you saying the surface of a black hole is like a giant cosmic hard drive storing all the information that falls into it?
That's a simplified way to put it, but you're getting the idea. String theory suggests that information isn't destroyed, but transformed and stored in the complex web of string vibrations on the black hole's surface. This is connected to something called the holographic principle, which says that information about a three-dimensional object can be encoded on a two-dimensional surface, like a hologram.
Wow, this is blowing my mind. So string theory isn't just about these tiny particles in extra dimensions. It's also giving us new ways to think about some of the biggest and most mysterious things in the universe.
That's the beauty of string theory. It connects the very small with the very large, weaving together seemingly different parts of physics into a unified tapestry.
Okay, before we get too lost in the cosmic tapestry,
Right.
I want to touch on something that came up in the source material. Parallel universes.
Okay.
That sounds like something straight out of science fiction.
It's definitely one of the most intriguing and speculative parts of string theory. Remember those extra dimensions we talked about? Well, one consequence of having them is that there could be tons of other regions of space-time beyond our own observable universe. Basically, parallel universes.
So you're saying there could be other universes right next to ours, but we can't see them because they're hidden in these curled-up dimensions.
That's the idea. And it gets even crazier. String theory suggests that these other universes could have different physical laws, different constants of nature, even different numbers of dimensions of space and time.
So imagine a universe where gravity is weaker or where time flows backward. That's wild.
It is. And while we don't have any direct evidence for these other universes, the math of string theory allows for the possibility. It really makes us rethink what reality even means.
This has been an incredible start to our deep dive.
Yeah.
We've gone from tiny vibrating strings to black holes as cosmic hard drives, and now to the idea of entire parallel universes.
Right.
It's a lot to take in, but it's super exciting.
I agree. And we're just getting started. There's so much more to explore in the realm of string theory.
This deep dive is really making me rethink the whole idea of the universe.
Yeah, it's pretty mind-blowing stuff.
Before we get into the more complicated parts of string theory, I wanted to ask about some of the criticisms. The sources mentioned that not all scientists are convinced about this idea. Why is that?
Well, you're right. String theory has its skeptics. One of the main criticisms is that it hasn't produced any predictions that can be tested with our current technology. It depends on things like extra dimensions and supersymmetry, which haven't been directly observed.
So it's like having this really cool map,
Right.
but no way to tell if it actually leads to the treasure.
That's a great analogy. This brings up another challenge. Actually, testing string theory is really difficult. The energy levels you need to directly see strings are thought to be trillions of times higher than what we can make even with our most powerful particle accelerators, like the Large Hadron Collider.
So we're talking almost unimaginable energy levels. But are there any other ways to try and validate it?
Oh, definitely. While directly seeing strings might be far off, physicists are exploring other ways to test parts of string theory. Some are looking at cosmic rays, those ultra-high energy particles that hit Earth from space, hoping they might hold clues about how strings interact. Others are analyzing black holes super closely, looking for tiny differences from Einstein's general relativity that string theory could explain.
So it's not a dead end. There's still a chance we might find ways to prove or disprove some of string theory's predictions.
Exactly. Science is a process of exploration and refining what we know. Even if parts of string theory turn out to be wrong, exploring it has already led to some big advancements and opened up whole new areas of research.
I'm noticing a pattern here. It seems like string theory is as much about asking the right questions as it is about getting definite answers.
I think you've got it. String theory is pushing the limits of what we know, making us confront some of the most basic questions about what reality is. It's a journey where the exploration is as important as the destination. And speaking of exploration, you mentioned earlier those extra dimensions.
Yeah.
Well, they also play a big part in another fascinating aspect of string theory: brain cosmology.
Okay, brain cosmology. You mentioned this briefly in part one. It's like our universe is stuck on a giant sheet, right?
Exactly. Imagine you have a sheet of paper floating in a room. That sheet represents our universe, a brain that's embedded in this higher dimensional space. We're stuck on the surface of this brain and can only experience the 3 spatial dimensions we know.
So we're trapped on this cosmic sheet, unable to experience the higher dimensions around us.
Kinda, yeah. Brain cosmology suggests there could be loads of other brains out there, each one a different universe with its own set of physical laws and constants. This connects to the idea of the multiverse we talked about, where countless universes exist along with ours, maybe even interacting in ways we can't even fathom.
So our universe could just be one slice of a much bigger, multidimensional reality. Makes you wonder what it would be like to experience those other dimensions. What kind of crazy things might we find?
It's a pretty amazing thought, isn't it? Even though we can't directly observe these other dimensions, the math of string theory lets us explore them theoretically. For example, some physicists think gravity might be weaker in these higher dimensions. This could explain why it seems so much weaker than the other fundamental forces in our universe.
So gravity could be leaking into these other dimensions. That's why it seems so weak here. That's a fascinating idea.
It is, and it shows how string theory is making us question our basic ideas about space, time, and gravity.
All this talk about extra dimensions and brains makes the universe seem way more vast and complex than we ever thought.
Absolutely. String theory challenges how we see reality, taking us beyond the familiar three spatial dimensions and suggesting a universe full of possibilities we're just beginning to understand.
But let's come back down to Earth for a second from this mind-boggling vastness of the multiverse and talk about something a bit more concrete. The math behind string theory, I know, is a big part of it all. Can you give our listeners a taste of how it works?
Sure. Math is the language of string theory. It's what lets us describe these complex ideas in a precise and testable way. One of the coolest mathematical tools in string theory is something called string duality.
String duality. Sounds intriguing. What's that all about?
Basically, string duality says that different versions of string theory that seem totally separate are actually just different ways of looking at the same underlying reality. Imagine looking at a sculpture from different angles. Each view is unique, but they all show the same object.
Different versions of string theory might look different at first, but they're really just different descriptions of the same fundamental physics.
Exactly, and this duality has helped physicists connect string theory to things like black holes and even the physics of the very early universe, linking together areas of research that seemed totally separate before.
That's fascinating. So string theory isn't just about these tiny strings vibrating in 10 dimensions. It's a framework that connects many different areas of physics, and maybe offers a way to understand the universe in a unified way.
You got it. It's this potential to unify things, to bring together gravity, quantum mechanics, and cosmology under one big theory that makes string theory so compelling.
But let's be real, string theory is a complicated and abstract topic. Is there any way to make these concepts easier to grasp, maybe with analogies or examples from the real world?
Definitely. Analogies are super helpful when you're trying to understand abstract ideas. One classic analogy for string theory is the cosmic symphony.
I think we touched on that a bit at the beginning. How does the symphony analogy help us understand string theory?
Imagine the universe is like a giant symphony orchestra. The different instruments represent all the different particles and forces that make up the universe. Just like different instruments make different sounds, the different vibrations of the strings create different particles and forces.
So an electron could be a high-pitched violin note, while a proton is a deep cello note.
Precisely. The interactions between particles are like the harmonies and melodies that come from different instruments playing together. According to string theory, the universe is a symphony of vibrating strings, constantly composing the music of reality.
That's such a cool way to picture it. It makes this complicated mathematical theory seem almost poetic.
It does, right. And it shows how string theory isn't just about equations and abstract concepts. It's about appreciating the beauty and interconnectedness of the universe at its most fundamental level.
Even with these analogies, string theory can still feel pretty overwhelming. What advice would you give someone just starting to explore this fascinating but challenging subject?
My advice would be to just enjoy the journey. String theory is a vast and complex subject. It takes time and effort to understand it. Don't be afraid to start with the basics, check out different resources, and ask lots of questions. There are tons of great books, articles, and videos that can help make these ideas easier to grasp.
That's great advice. And I think that applies to learning anything new and challenging. The most important thing is to be curious, ask questions, and enjoy the learning process.
Exactly. At its core, string theory is all about asking big questions and trying to understand more about the world around us. That's something we should all try to do, whether we're physicists or just curious people wanting to learn more about the universe.
Speaking of big questions, one of the most mind-blowing parts of string theory is the idea of parallel universes. We briefly talked about this in part 1, but I'd love to dig deeper into the different kinds of multiverses that string theory suggests might exist.
Sure. The idea of the multiverse comes from a few different aspects of string theory, leading to different models of what a multiverse might be like. One popular model is the landscape multiverse. This comes from the massive number of possible solutions to the equations of string theory. Each solution represents a different universe with its own unique set of physical laws and constants.
So it's like string theory allows for a huge range of possible universes, each with its own rules.
Exactly. Imagine a vast landscape with mountains and valleys. Each valley represents a stable universe, while the peaks are unstable configurations. Our universe might just be one valley in this huge landscape of possibilities.
That's an incredible image.
Yeah.
It makes the idea of the multiverse seem almost real. Are there any other multiverse models that come from string theory?
Another cool model is the brain multiverse, which comes from brain cosmology. Remember that analogy of the universe as a sheet of paper floating in a higher dimensional space?
Yes, the idea that our universe is a brain embedded in a higher dimensional space.
Right. In the brain multiverse, there could be countless other brains out there, each one representing a different universe. These brains could even collide or interact in ways that might have effects we can observe in our own universe.
So these other universes might not be totally separate. They could bump into each other, like ships passing in the night.
That's the idea. Some physicists even think these collisions might be why our universe looks the way it does, things like the cosmic microwave background radiation or how galaxies are spread out.
That's amazing. It makes you think there might be clues about these other universes hidden in the data we already have about our own.
It's an exciting thought. It shows how studying string theory leads us to consider ideas that used to be pure science fiction.
The multiverse definitely falls into that category.
Yeah.
But let's be honest, the idea of countless other universes can be overwhelming. How do physicists even begin to wrap their heads around such a huge and complex concept?
It's definitely a challenge. One way is to focus on creating mathematical models that describe different types of multiverses and then explore what we might be able to observe because of them. Another way is to look for indirect signs of other universes within our own universe. For example, some physicists believe that collisions between brains could leave behind specific patterns in the cosmic microwave background radiation, which is like the afterglow of the Big Bang.
So it's like searching for cosmic fingerprints that might hint at other universes.
Exactly. It's a tough job, but the payoff could be huge. If we found evidence for the multiverse, it would completely change how we understand the universe and our place in it.
It's mind-blowing to think about all the possibilities string theory opens up. We've gone from tiny strings vibrating in 10 dimensions to these vast landscapes of multiverses crashing into each other. It's a journey that's both challenging and awe-inspiring.
I completely agree. String theory is pushing the limits of what we know, forcing us to confront the biggest questions about the nature of reality. Even if we never have all the answers, the search for knowledge is worth it.
Speaking of the search for knowledge, string theory has led to advancements in lots of areas of physics and math. Could you give our listeners a taste of some of the most exciting things that have come out of string theory research?
Of course, string theory has had a huge impact on many areas of physics, not just particle physics and cosmology. For example, it's given us new insights in condensed matter physics, which studies how matter behaves. The mathematical tools developed for string theory have been used to understand things like superconductivity and superfluidity.
So string theory, which tries to explain the universe at its most fundamental level, is also helping us understand how materials work in our everyday world.
You got it. It just goes to show how connected science is and how even abstract theories can lead to practical applications. Another area where string theory has made a difference is in quantum computing.
Quantum computing. That's really interesting. How does string theory connect to that cutting-edge field?
Well, the math of string theory, especially the idea of string duality, has provided insights into quantum entanglement. Entanglement is a crucial resource for quantum computers. This connection has sparked new research into developing algorithms and architectures for these computers, which could lead to revolutionary increases in computing power.
So string theory, which started as a quest to understand the tiniest parts of matter, is now helping develop technologies that could change our world.
Exactly. It reminds us that scientific exploration often takes us down unexpected paths, and discoveries in one field can lead to breakthroughs in others.
Wow, it feels like we've been on this incredible journey, through the cosmos.
Yeah.
Talking about everything from these tiny vibrating strings
Right.
to like the vastness of the multiverse.
It has been quite the deep dive. Yeah, into some pretty mind-boggling stuff.
Before we finish up, I'm curious about something. We've talked about how string theory might unify different areas of physics and maybe explain these things we don't fully understand yet.
Right.
But what about its impact beyond just theoretical physics?
Yeah, that's a great question. While string theory is still mostly theoretical, It actually has had a surprising impact in other areas like mathematics.
Math.
Yeah.
That makes sense, I guess, with all the math involved in string theory.
Right.
But how has it actually changed math?
String theory has actually led to some breakthroughs in fields like algebraic geometry and topology. For example, it's given us new ways to understand complex shapes and spaces, which has led to advances in things like knot theory and studying higher dimensional geometry.
So string theory, which is about the universe at its tiniest scales, is helping mathematicians explore the properties of shapes and spaces in new ways.
Exactly. It's a really cool example of how abstract theoretical work can have unexpected consequences in other areas.
It really shows how connected different scientific fields are, doesn't it?
It does, and it highlights why it's so important to support fundamental research, even if we don't see practical uses for it right away. You never know where a scientific journey might take you.
Speaking of journeys, string theory has been on quite a ride since it was first proposed.
Yeah, for sure.
It's had its skeptics and challenges, but it still fascinates physicists and the public. What do you think the future holds for string theory?
Well, that's a question that causes a lot of debate among physicists. Some think string theory is close to a major breakthrough, maybe with some new experimental data or theoretical insights. Others are more cautious, saying that its inherent difficulties might limit what it can predict.
So it's a field with a lot of uncertainty and debate.
Absolutely, and that's part of what makes it so exciting. String theory is pushing the limits of what we know, making us grapple with these fundamental questions about reality. It's a journey where the exploring is as important as the destination.
It's been an incredible journey for us today, too.
Yeah, it has.
We've explored some pretty amazing concepts.
Right.
From the idea of tiny vibrating strings to these vast multiverses.
Definitely.
I hope our listener enjoyed this deep dive into string theory.
Me too.
It's a subject that will keep sparking curiosity and wonder for years to come.
I think so too.
If our listener is interested in learning more, where would you point them?
There are a bunch of great resources for people who want to explore string theory further. A good place to start is Brian Greene's book, The Elegant Universe. It's a pretty accessible and engaging introduction to the subject. And if you're more into math, there's some great textbooks and online courses available too.
And of course, the journey doesn't have to stop there.
Right.
There are tons of articles, scientific papers, and even other podcasts out there all about the mysteries of string theory and the universe.
Exactly. The most important thing is to keep asking those questions, keep exploring, and never lose that sense of wonder about the world around us.
Well said. To our listener, thank you for joining us on this deep dive into the fascinating world of string theory.
Yeah, thanks for listening.
Keep exploring and keep looking up at the stars because the universe is full of wonders just waiting to be discovered.